Hi there. This is the second segment for Lecture 1 in my lectures, David Dye's lectures in MSE307 Engineering Alloys. And in this second segment, we're going to talk about two things. One, jet engines and how they work and what the stresses and temperatures are for different components, what we call different bits of the engine, what the drivers are in optimizing those and developing those materials. Then we'll talk a little bit about how we life components that have some pre-existing assumed defect distribution in them, be they casting inclusions or ceramic inclusions or whatever it is, some defect distribution that we assume in calculating a lifetime. Why do we do this? So thinking a bit about this company, Rolls-Royce, they are the UK's largest exporter, the UK's largest export business, including all the invisibles, any invisible earnings from banks and so on. They are a big company. They are. This is 2011 figures for the 2010 year. They have a market cap of some tens of billions, something like 15 billion. They're in the middle of the FTSE 100 index. They have about 11 billion in earnings a year, which is about 0.5% of UK GDP. 1 in 200 pounds of productivity in the UK comes from this company. It's about 2/3 of those earnings are civil. They do have some defence, military engines and submarine reactors, but mostly they're a civil gas turbine company. The car company is actually owned by BMW and is based in Kent, and is nothing to do with this corporate, apart from they share the brand name, which these guys own the rights to. They have about a 10% operating margin and about a 5% net profit margin. And that's quite important. And they have about half of the worldwide gas turbine market for twin-aisle airplanes. They're not in the single-aisle airplane market anymore. And GE have about the other 45%, and the rest is some bits and bobs from some other companies. And they have about 22,000 UK employees and about £260,000 a year revenue per employee, which is a very high number. And the area they're based in, the East Midlands, in large part because of them, has one of the highest gross value added per employees in the country. That means that's the driver of what makes you a rich company, as a rich region, or a rich economy as a country. And about half of their revenue is actually service revenue associated with keeping those engines flying. Only a minority of it is making the new engines. And they spend about £1 billion a year on R&D, which is a really big deal because they have this profit margin. And that is the thing that makes the world sing for us as research scientists. That means they have the money to develop new materials. So one problem, for instance, with the steel industry or the aluminium industry for beer cans, window extrusions, cars for steel, rebar for buildings, the profit margins there are very, very small, and so there's not a lot of money to invest in R&D despite the very large tonnages. Whereas these guys, the gas turbine industry, like the nuclear industry is another example, they have a high consequence of failure. They have big drivers to make the best materials they possibly can, and therefore to be able to push those to their limits safely. And therefore that means they have a large driver for making better materials, and they have the money to make that happen, and therefore to pay for research scientists. And they deliver something like 1,000 engines a year. So this is not a big number. If you're an auto manufacturer, you start getting excited if you deliver more than 100,000 cars a year, not 1,000 engines a year. So this is a relatively speaking small production. And Rolls has expanded a lot in the last 20 years, so they have a fairly young fleet, which also means that they have quite a long service base that will come and that gives them growth in the future. So as we said before, how do jet engines work? First, airflow comes into the front of the engine. Then we have a fan. A lot of the air goes around the outside, driven by this fan, which is held in this duct here. So we have a casing here that can contain the blades if they come off. It can't contain the disc that the blades sit on if it breaks, because the disc weighs too much and has too much energy contained within it, too much kinetic energy. Then we have a compressor that starts off at low pressure, and as we compress the air more, the pressure goes up, the temperature goes up, and eventually come into some combustion chambers here where we mix with fuel, and then as the gas escapes out the outside and gives us a jet at the back, we extract some of that energy in these turbine stages, which we use to drive the fan. So the high pressure turbine drives the high pressure compressor, then on one shaft, and then on an inner shaft to that we have a low pressure turbine which drives the fan. And that's it. That's the design of the engine. Here for the Trent XWB, here's how it's laid out. So you have all of these low pressure turbine stages driving the fan, this one stage of the turbine driving the IP, intermediate pressure system, and the high pressure turbine there driving the high pressure compressor. So you have 3 sets of shafts in this Rolls design. GE used 2 shafts. That means that they can only have 2 spindle speed settings, which means that they're less optimal for more of the stages, and it means they tend to have more stages, but then they don't have to carry around a 3rd shaft. So, you know, Rolls-Royce people, designers will argue this gives you a more scalable engine architecture. But you probably have to do 2 shaft if you want to make a small engine. It's an optimization study for mechanical engineering, essentially. But it's one of the things that's different about Rolls. And the thing to notice, therefore, is also the speeds are very different. When you have this big fan blade here, you've got big centrifugal forces, and so you need to be at relatively low speeds if this isn't going to be supersonic. So that takes you down to 3,000 RPM, whereas here you'll go up at 10,000 RPM, you're much faster. And those are big speeds. They're not big speeds relative to something like a supercharger or turbocharger. Turbochargers get up to 100,000 RPM, but they're much smaller. And small jet engines spin very fast, but big engines, you know, you're limited by things being supersonic and by the sort of centrifugal forces you can handle. And that means you're at a mere 10,000 RPM, but that's still pretty fast, right, for a big structure. So that's a big number. In terms of temperatures and pressures as you're going through the engine, this is a graph as you go through, you build up pressure, and things soak, and then the pressures drop. The temperature gradually increases, you pressurize the air up to maybe, this is a very old slide, back end of the compressor, you're at maybe something like 850 degrees C, or you'd like to be. For the blade temperature, a bit lower for the discs that are hanging on. This is a depiction of the discs that are hanging on. Then you inject the fuel, burn it. The gas stream temperature then gets up to above the melting point of the alloy, and you have to protect by bleeding cooling air over the blades. And then that temperature drops as you come across the turbine as you let the gas expand, of course. You also have a gradual, as you squeeze the air, you have a gradual reduction in the velocity of the air that way. And then it accelerates again as you let it out through the turbine. That's how it works. So as you get hotter, of course, you run into the problem that the temperature capability of the alloy is limited. So you use titanium here for its good specific fatigue strength. That is its fatigue strength per unit weight. That is its strength under a fatigue load, which was much lower than its yield stress. So you use titanium, and its specific, its density is 4.5 rather than 8 for a steel. So that tends to take you towards using titanium at the front end. And then at some point, you exceed a temperature of about 550 to 600 degrees C, and you transition into nickel. And that tends to be in the HP compressor here. And a lot of them now, you have an all-nickel HP compressor. And then that's when you start to need the creep resistance of nickel superalloys and the very good high temperature strength, given by the remarkable properties of nickel superalloys. And then you're all nickel out the back here. Down through here, your shaft temperatures are probably a mere couple of hundred degrees, and there you're using very high strength VAR steels, things like Jeffeat, which is making up the shafts. And then this casing here, that could be titanium, that could be a Kevlar composite, various options. It slightly depends on, well, it changes from engine to engine. The designers haven't really figured it out yet, figured out the optimal set of trades. So different things get used in different engines for the casings. And just to give you some typical operating temperatures and stresses, for the fan blade at the front, you're at a temperature anywhere from -60 to +80 degrees C. Let's say it's 40. You have a peak stress there, which is about the run-out fatigue strength of the alloy, about 550 MPa. And that will last something like 10,000 cycles, because there will be erosion from the being grit blasted by the sand in the air, essentially. Then as we come into the compressor, we'll get hotter. The stresses will probably drop a little bit, but not much. And they'll last again 10, 20,000 hours, slightly depends. we go to the disc that blade is hanging off, actually we go a bit further in, we're then at the HP, so we've gone, that's an IP blade I was talking about here, and here in the HP, in the nickel, the sort of temperatures at the rim are more like 750 degrees C. And there the stresses we have to drop down because of creep, and they might be something like 400 megapascals. Still a pretty chunky stress. At the bore of the disc, it'll be cooler, and so we can run to a higher stress. And so the rim here is limited by creep and fatigue, and here we're just limited by fatigue. Here we're limited really by LCF and HCF, and here we're in nickel superalloys. Here in the disc here, sorry, that should be a disc rim. Sorry, that should be a disc blade. It's a disc. Yeah, ignore the blade there. That's it out of an alloy like Ti 6246, an alpha beta alloy. And here in the HP turbine, we actually go to using blades that are single crystal superalloys. So this is a single crystal superalloy. And at the skin of the metal, after we've gone through the bleed air and the thermal barrier coating, we'll be up at the maximum usable strength of the alloy, something like 1100 C, but the stress will be relatively low, 200 or so MPa. In the core of the blade, where it's shielded by the cooling air, we'll be down at maybe 650 or 700 degrees, but the stress will then be a lot higher, something like 700 MPa. And so there'll be a balance of stresses and temperatures across the blade, which will in part depend on how they shake down during creep. So there are a variety of conditions here that give rise to a variety of phenomena that are life limiting for the different materials, which is what we'll study in the course of this course. And what are we aiming to do? Well, we're aiming not to have that. That's a B-52, first flew in the 1950s, and it's smoky. And if you go and stand outside an airport and look at an old airplane, probably an old military plane, because they fly the oldest rust buckets, you will see as they take off, sometimes they are literally quite smoky. There are a lot of emissions coming out of these guys. That's unburnt hydrocarbons. What you're seeing there is the smoke, but that also goes with NOx and SOx and all the other things, and they're noisy. Whereas a modern aircraft is relatively quiet, doesn't have the smoke, has relatively less NOx and SOx, and a lot less CO2. So since 1950, we've reduced the fuel burn by about 70% per passenger mile. And the goals for 2030 and 2050 relative to today are something like triple the passenger kilometers is what we're expecting. And the problem with that is that as we decarbonize electricity and road transport, then what that means is as air passenger growth is something like 5 or 6% a year worldwide, because we're making it cheaper, because the world economy is growing. If we're only making air transport 1% a year more fuel efficient, well, 1 or 2%, well, then aviation is going to then be a large fraction of our total emissions as a society. And it's very difficult. Kerosene has the highest energy density of any fuel. Things like hydrogen storage are never going to get there. Batteries are never going to get to the sorts of energy densities, energy per unit mass that kerosene has. And so the only thing we're going to be able to do here to ameliorate the CO2 is things like biofuel. That is by using fuel that we grew from trees that suck the CO2 out of the atmosphere in the first place. Because we can't substitute here. So there is a big environmental and ethical driver to make these things more fuel efficient as well. So that's the motivation ethically as well, to make better jet engine materials and better engines. So that's sort of how the engines work, which will motivate the sorts of temperatures and stresses we're thinking about through the course. The other thing we're going to think about a bit as we start the course is about an air accident, and therefore how we develop a life from a material and what defects arise, and how we melt and forge things to avoid defects. So one thing I want to talk about now for a little bit is lifing. What we've done before, what you've done previously in second year, is you've looked at fatigue crack growth curves. So that's fatigue crack growth, rate of crack extension dA per cycle n, against the stress intensity factor, delta K, where delta K is sigma times root, or delta sigma, the varying stress, times the square root of pi times the crack length, A. And in this region, you obey the Paris law that you saw in second year. The ADN is C times delta K to the M, where C and M are some constant. and plotted on a semi-log plot like this, that would then be a straight line. There'll be a threshold stress, oscillating stress below which you wouldn't grow a crack. If you don't stress it, the crack won't grow. And there would be some threshold here where you got to K1C and the crack got so big that it just went bang. And the sort of test piece we would use would be one like this. We'd have a knot. We'd see how it grew. We'd have a little plastic zone in there. And what we'd like to do is figure out how to use this to determine a life given a pre-existing defect distribution. So the first option for lifing is if you know what the defect distribution is, particle density against size, arrange for the stress to be low enough that for the largest defect, then you're below the threshold delta K. Then it will be safe, for sure, forever. The problem is, what's the largest defect? Now you might say, well, okay, if I've got some volume of metal, I can read it off this graph. But if I make this a log plot, actually, for some particle density per meter cubed, that 10 per meter cubed, well, then I'm at a 0.5 millimeter defect for this distribution, which is off the end of this scale. And that, creates a problem. How do I actually examine that much material, which we'll come back to. And this is a typical distribution for a PM nickel superalloy, Renault 95, GE alloy, so I've taken from the literature. But say you knew what that probability distribution was like, we could then go through a procedure a bit like this. We could set a desired failure rate, something like 1 per 10 million takeoffs, say. We can determine a replacement rate of our material, so that's every 60,000 hours or 8,000 cycles, 8,000 flight cycles, will replace the material. So that is 1 in 10 million multiplied by 8,000. That gives me a volume of, if I know how much material is in the engine, say 2 tons of material, I can then determine how much material I need and what probability that then gets me to. And then I can look up on my probability distribution what the implied largest inclusion is, and then look up the stress on the DADN curve. And the problem is, if I go through that exercise, I'll end up looking at an inclusion that's on the order of 0.5 millimeter. And therefore, the stress that I will be able to safely tolerate will be very low. And therefore, I would end up with a very heavy jet engine and a very heavy plane, and I'd never get off the ground. And certainly not with an engine that would be efficient or saleable. So, and notice that while I've called this deterministically safe lifing, it's still from a probability distribution with a desired failure rate, right? And that's problematic, right? We're now assuming a failure rate, and people don't like that, right? If we go to a court and say, well, we accept that, every, once a year, we'll lose a plane. People hate that. People really hate that because it sounds callous. They're okay with taking a risk of walking their child out on the street and being knocked down by a drunk driver because they feel in control. But they don't like government or corporations taking those risks for them where they don't get to have any control. And courts tend to penalise that, especially in the States, very heavily. So this is, you have to go with a probabilistic approach probably, but people don't like it. And so we try and make this number very, very low such that that effectively means never. What the industry has historically done is they've taken an empirical approach based on testing. So if you assume that the life distribution is log normal, and you spin test a component until you get to a crack length that you can find by non-destructive inspection, it's about 0.75 millimeter. Do that 6 or 8 times till you find a mean and a standard deviation for the life to that crack length. You can then decrement that by a factor of 3 sigma. If you know the uncertainty and the average, the mean, you can find the minus 3 sigma life, which if it's a log normal distribution of lives will be the 1 in 750 chance of failure. And that slightly depends on how many tests you've done, but for something like, for that sort of number of components, 3 to 8 components, that tends to be about a third of the life. So if you had a 60,000 hour mean life that you found in spin testing, this would give you a 20,000 hour life. You have another safety factor there, which comes from growing the crack from 0.75 millimeter to failure. It probably isn't a very big safety factor, but it's some. And if you then run through the volume of material you have, and so on and so forth, that actually ends up being about 1 in 10 million takeoffs when you run the numbers through, which I do in the notes. The problem is that this empirically works. You don't need to know anything about material science, which is the sort of appeal to mechanical engineers and to safety people. The problem is that it's actually slow. You can only do it when you've got some discs that you've designed and you're willing to spin test. It costs you something like £250,000 per spin test, so this is also very expensive. And you can only do it once you've designed the discs and manufactured them at scale, so you can't ask yourself, okay, that didn't give me the life I expected, I need to get a bigger life, so I need to drop the stresses, so I need to redesign, and then you have to go through another 12-month design process at the end of your engine design sequence. So this is very expensive and slow and creates a lot of program risk. So you'd rather not do it. Actually, people do it, but they do it as a confirmation that they've done everything right up to that point. What people do in design is they want to do something more intelligent using fracture mechanics. So just as a reminder, in fracture mechanics, we take the Paris law, where delta K is the oscillating stress intensity factor. Delta K is some number y, about 1, times the oscillating stress, the maximum minimum stress is times the square root of pi times the crack length. So we can put the crack length in there, so that becomes cy delta sigma root pi a all to the n. We can then separate, take dn up there, and take this guy down there, and that will give us this. To make this chart, we can take logs and then get a straight line in order to find m and c. But that's an aside. If we take that down there and up there, we can then integrate from a life from our first cycle to our cyclic life NF, from our initial crack size to our crack size for final failure, and that would give us, when we then integrate, a final life. And then we merely need to know the material parameters, C and M, Y potentially, so we'll call it C2 then, C1. I'm just forgetting about the factors. I need to know the stress, which I get from my design calculations, and I need to know the initial floor size and the floor size at which we break. Again, I can get that from test pieces. So what's my initial floor size? But if I knew that, I could then predict a life. And what we can then do, one option is what's called retirement for cause, or damage tolerant lifing. And this was pioneered by the US Air Force in the 90s on the F-15 fleet. And the idea here is, if you assume that the initial crack size is the smallest crack that you couldn't quite see with non-destructive inspection, then you can find out what the life would be until you got to a crack that would fail. So you can find the critical crack for fast fracture and find out how many cycles it would take you to get from the initial floor size ANDI to A crit. To get from there to there. And then that sets your inspection interval. So if you started off assuming a crack was that size, it would hypothetically go up to there, and then you inspect. And when you inspect, if you find no cracks, you can then reset your assumed maximum crack size to the non-destructive inspection amount. And then you can grow the crack again, the hypothetical one, inspect again, find nothing, keep going until you eventually find a crack, and then retire the disc. Okay, so compared to this spin testing, the problem with this is that most of our components here we would retire at a small fraction of their actual life. Yeah, 749 out of 750 of the discs we would retire early, and therefore we'd spend a lot of money with the jet engine companies making unnecessary material, which is great if you're a jet engine company and bad if you're a taxpayer. So this approach means that we only retire things when we have cracks in them. And if they don't have cracks in them, we don't retire them. So practically speaking, what we do is we set an inspection interval and then find the smallest crack that will grow to failure. And then we ask if that's bigger than the smallest detectable crack and say it would be safe. So if we take a nickel superalloy with these properties, then the A crit would be 11 millimeters. If we wanted a 10,000 cycle life, we need the non-destructive inspection to be sensitive to cracks of smaller than 0.3 millimeters, and then we'd be okay if we inspected every 10,000 cycles. So that means there's a big driver to make non-destructive inspection more sensitive, and there's a strong driver to make the fatigue crack growth rate slower. So our material parameter that we want to optimize now becomes the fatigue crack growth rate in the Paris law, not its toughness, not its initial defect distribution to some extent, but the NDI sensitivity and the fatigue crack growth rate. Those become the things that drive our performance. There's a problem though, which we'll see when we look at the Sioux City accident, which is that this assumes that every crack is found. And it ignores the possibility that in taking it apart and inspecting it and putting it back together again, we may actually damage the component. But the US Air Force has 20 years experience now of this approach and making it work. So at least in the military context, it can work quite well and has saved them an awful lot of money. There are some special factors. The US Air Force, like most air forces, like any air force, is limited in the number of hours they fly their planes because they only really, in peacetime, need to keep their pilots qualified. The rest of the time, they don't want to spend the money on the fuel, and they don't want to put the life on the airframe, so they have the thing on the ground, and they need to keep the techs busy, so they keep taking it apart and look at it and put it back together again. So they can afford to inspect frequently. Also, they go through funny flight cycles where they might want to inspect just to check they didn't break it, and they take their planes to funny places where they might ingest funny things, dust, air, things from deserts. And so again, they tend to take their engines apart quite often, and that doesn't affect their operational tempo because they're at peace. So they can do this quite frequently. The other thing is the military tends to be a well-indoctrinated, well-trained organization with good, effective staff. And thinking about the nuclear example, the US Navy has a very long track record of operating nuclear reactors very safely without having the sort of problems that the civil nuclear industry has had in the US, with operators not necessarily following all of the checks that have been mandated. So there you have a good example in the nuclear industry where the civil industry has struggled and the military has apparently not, with compliance with the regulations that are in place. I don't want to take that too far because we haven't had the same sort of problems, it would seem, in the UK, for instance, in the civil nuclear industry. And of course, you don't know what goes on behind the box in the military because a lot of things are secret. So let's not push it too far. But there are certainly differences between the military experience and the civil experience that mean that the military can probably apply this in a way that you can't when you want to fly engines every day and you're EasyJet. So a fourth option is what is called probabilistic lifing, and this has been developed in the academic world in the last 20 years. And here, what we do in the academic world is we test small test specimens, small things the size of my finger. We test small volumes of material. And when we fly an engine, of course, we fly a large volume of material. And so our stress life curves that we do in an academic lab with test specimens, we will find that our test specimens fail from initiating defects that are things like the microstructure that are probably unrepresentatively small compared to the things that fail large discs, because there's just much more chance of there being a large inclusion in a large disc. So what we would have to do to correct for that is we'd have to know the defect size distribution and the fatigue crack growth curve, and then we could calculate a safe life based upon the real probability distribution of there being a defect in a large disc and the fatigue crack growth behavior. And that's going to be a very attractive approach when ceramic inclusions, for instance, or gas porosity may be present. So what we do is, for each initial defect size in the probability distribution, we would evaluate the time for it to grow to a threshold maximum size, and then based on our tolerance for risk, make the defect probability distribution and the volume we have, estimate a life. And we could then incorporate mitigation actions like NDI that have a probability of finding the crack. So we could then incorporate a probability for success in NDI. We could do that in retirement for cause as well, actually. But we could then have a, say, not NDI, a 95% chance of finding a crack of bigger than a given size, but maybe it didn't work that day or something. And we can then reduce the probability of large defects. We can change the probability distribution based upon our inspection regime. And that we can do that without assuming that non-destructive inspection is perfect. And we can incorporate periodic inspection in a similar way and get an overall philosophy for lifing. Obviously, it's going to be complicated. But there are some consequences of that. When you do that sort of approach, then large volumes, you would say, would fail earlier than test pieces. So that's the number of cycles in the life and the probability of failure. According to this sort of approach, then a specimen might have a very long life compared to a small disk or a large disk. So a large disk would automatically have a lower life than a small disk, for instance. So large compressor disks compared to small turbine disks you might have to decrement the stress in them in order to achieve a similar life, simply from the volume of material and the probability distribution of defects. The other thing is that the defect giving rise to failure will be, as what we just said, smaller in a test piece than a disk. That is, the test piece is testing a smaller defect distribution, and so the test piece may be unrepresentative of the mechanisms of failure, which is also worrying. This is data for 718 at a stress of 1050 MPa, and this is for a given inclusion size what the 90% probability of failure distribution would look like, given some assumption about the intrinsic defect size distribution. The other thing is that if you're inspecting, if you have a given volume fraction of defects, of inclusions, and a given size of them, you can read off how much material you must examine in order to have an 80% confidence of finding one. So, for instance, if you have a volume fraction of 10 to the minus 3, 0.1%, 10 micron defect, you would have to examine 10 millimeters squared of material in order to find, to measure that volume fraction correctly. If you were talking about a volume fraction of 10 to the minus 5, on the other hand, then you would need to examine for 50 micron defects, something like 10,000 millimeters squared, which starts to feel like a lot of optical micrographs. Starts to feel unfeasible. And that means that we really want for unlikely but large defects to have a volumetric inspection method, something like X-ray radiography. And then you get into, well, okay, if I've got a section that's so thick and my inclusion doesn't absorb X-rays at all, and I've got a sensitivity of 10 to the minus 3 to variations in the overall intensive transmission of X-rays, then what sort of defect can I see with my radiography? And maybe you end up doing tomography instead. But you would make a similar chart for a volumetric inspection method, and that could in principle mean you can be a lot better at finding defects. And that takes you towards using a range of inspection methods. The other thing you can do if you want to find a defect distribution is you need to find a way to concentrate them. So one way of doing that for ceramic inclusions, they're lighter than the metal, so they'll, oftentimes, so they will tend to float to the surface, given an opportunity to do so in a relatively still fluid in the melt. So you take some material and you remelt it to make a button, called electron beam button melting, and then let them float to the surface of the button, concentrating them, which then means you can characterize them in your SCM because you've got a relatively controlled area to study, and that allows you to make the defect distribution. So that's one way of measuring defect distributions practically. So that's a bit of a view on how lifing works in the general case and how jet engines work. And the big thing there is we need to know the inclusion distribution. We need to be cognizant of what defects our manufacturing process will put in place and the sort of frequencies of them. So, for instance, in laser additive or EB additive manufacture, people say, oh yeah, we can produce 100% dense parts with no defects. You say, really? You're consolidating powders with no gravity and no compaction. Is that really the case? And the answer is, well, if I say I want to have a probability of there being 10 micron pores of being less than 0.1% in a volume of a meter cubed, they are a million miles away from that sort of defect rate. Yeah. So EB additive manufacture cannot today produce very fatigue-resistant parts. They can produce 100% dense parts that have some fatigue strength, but they haven't really got the defects out in the way that you do in a traditional ingot metallurgy process with vacuum refining and forging. And so what we're going to do in the next lecture is we're going to look at the traditional manufacturing sequencing and how it gets rid of those defects. So I'll see you next time.